All right, so we've seen what happens when you exert a force or multiple forces on an object. You can either be all in equilibrium and your object will stay where it is, or you can have a constant motion, or you can have a net force causing your object to accelerate. And of course, one of the things that you can accelerate is yourself, like this guy riding his bicycle. Just exerting a force will then result in an amount of displacement. And what you typically will use in everyday life when describing this is not the concept of force that you've exerted, but the amount of work that you've been doing, or the amount of energy that you've been putting in. Right? This guy riding his bike is exerting a force to make sure that he goes forward, and therefore he moves a certain distance. Right? So work, in the physics sense, measures how hard and how far you push. Right? Or in other words, work is force times displacement. We measure work in units of joules, and 1 joule is 1 Newton, a displacement of 1 meter for a force of 1 Newton, or 1 Newton meter. Now, not all forces, though, result in work. Right? Consider these 3 situations. On the left, we have someone pushing a car, very similar to the guy riding a bike. This guy is doing work. In the center, we have this lady pulling her suitcase. And she's doing some work because she's pulling the suitcase forward, but she's also exerting a force in the vertical direction. But the suitcase is not moving in that direction, so that part of the force is not generating any work. And finally, the guy on the right. He's carrying a tray, but is he doing work? Well, he's moving the tray in the horizontal direction, but there's no force there. So at least from a physics point of view, this guy is not doing any work at all. So to get the actual amount of work, what we need is the component of the force in the direction of the displacement. Fortunately, calculating that is pretty easy. Right? We project the force on the displacement. That simply gives us the force times the cosine of the angle that it makes with the displacement. Right? So to calculate the work done is you take the force times the displacement times the angle between them. That sounds pretty easy, but in many cases the force is not a constant. Right? Then what happens? Right? So suppose you have a force that looks like this. Can we still calculate the work? Well, to see how to do that, let's take a simpler example first. Suppose we have a force that's constant for a while, and then is some different value for a later piece. Then it's pretty easy. Right? We simply calculate the work for each of the pieces and add them together. All right, so that trick we can repeat. Right? No matter how many pieces we have, if the force is constant in each of the pieces, we can simply add them all up. Now, in our example, however, we had this curved line. Right? The force is not constant anywhere. Of course, we can approximate, right? We can divide our interval in small pieces and say, well, for each piece, the change in the force is really small, right? So what we can do is calculate the amount of work in each little piece, right? And then approximate the total work by adding these all up. And now if we make the pieces smaller and smaller, this approximation is going to get better and better until the point that we have infinitely many, infinitely small pieces, and we actually have the exact solution. And as you hopefully learned in math, that means that your sum becomes an integral. So really, the work is the integral of the force over the displacement, and of course there you take the component of the force along the displacement. So to show you how that works, let me give you a real-life example. In the previous unit, I showed you what happens if you have a block on a book, a horizontal surface. Now let's try this spherical or almost spherical surface. What happens then? Well, if I put the block on top of the sphere, right, we have a force balance like we had before. But if I tilt the sphere a little bit, well, initially there will still be a force balance because of friction. But if I tilt the sphere enough, the block is going to slide down the sphere. And as it slides down the sphere, what happens is that, well, the force of gravity is not going to change. Further down the sphere, gravity is still the same amount acting on the block. But the direction of the displacement is changing. Initially, right, the displacement was horizontal. It made a 90-degree angle with the force of gravity. And just like the waiter carrying around this tray, not much work was being done. And I actually had to tilt the ball a little bit to make the block slide in the first place. However, once it started sliding, right, there is a component of the displacement that's along the force, or a component of the force that's along the displacement, same thing, and then we get work done. Right? So if we want to calculate what this is, well, here we can use the same trick. We can say the amount of work for a small displacement is the force of gravity, m times g, times the cosine of the angle, times the magnitude of this little displacement along the surface. And now we can integrate, and what we find is that the work depends on the total angle that you covered and the radius of the sphere. And in particular, if you've gone full, the full quarter circle, right, you'll have m times g times r, which is something that you'll find come back later. Now, this work is a net amount of work done. Right? There's a force that has accelerated our object. Right? And work is a form of energy. An accelerated object still has this energy somewhere. It's stored in its kinetic energy. Right? So a net amount of work is generating a kinetic energy because it's accelerating the object. Now, of course, you saw that the block wasn't sliding from the start. Not when it was perfectly poised, but also when I turned the ball a little bit, it wasn't sliding yet. And of course, that's because of friction. And so frictional forces can also do work, or rather they can prevent work from being done. Right? Frictional forces are always along the surface, so they're always, well, parallel to the displacement, but in the opposite direction. Right? So they're, as it were, we're generating negative work. Right? So we can include that in our expressions and get a net amount of work, that's the work done by gravity minus the work that would be done by friction. And that's the amount of work that gives you the change in kinetic energy. And by applying this concept, you can actually include friction in your calculations pretty easily and find out how much work is done by friction and how fast, for instance, this block was moving when it was falling down from the ball. All right. In the next lecture, we're going to combine this concept with the concept of potential energy and arrive at the famous conservation of energy law that is the foundation of much of physics.